All right. How did this last week treat you? Or the last few days treat you?
Okay.
Just
Like
okay, huh?
now, just okay. I didn't get my fluids done, but I got my thermodynamics.
Okay. Okay. Thermodynamics got done. So with thermodynamics, we can talk about that for a bit, actually. Before I do some like quizzing, what what questions do you have about thermodynamics?
Do we use that equation Q equals ML on the exam?
Q equals MM,
L.
ML. Not really.
Okay. So I just
No,
understand.
big ones are Q equals um MCAT and Q equals um is it cat?
I don't know why I can't find the drive that was sent to me with by the source.
The drive that was sent to you from one source.
Mhm.
Have you if you go into your Google Drive,
Mhm.
you can go to shared drives,
Mhm.
or you could go shared with me and then search. Let me see which one it's shared with.
And then what is it labeled under one source, right?
Um, it would be labeled under it's just your name.
Oh wow.
Mhm. Okay. I do want to preface today with that I am ill. Um, so I'm a little sniffly today, sorry.
That's fine.
Um, but yeah, let's talk about some thermodynamics. We don't really use Q equals ML. We do use uh pretty frequently Q equals cat MCAT and Q equals cat. Um, yeah, we don't really use latent heat. Any other questions about thermodynamics before we dive into more?
Mhm.
Okay. Then let me ask you this: what is Newton's first law?
um, Something in motion is always in motion, and something at rest is always at rest.
Oh,
Am I
excuse me.
wrong?
What's that?
Am I wrong?
Um, no. No,
Oh.
sorry. I was choking.
Oh.
Newton's first law. Absolutely. Object in motion stays in motion. Object at rest stays at rest unless acted on by an outside force. Um, Excellent. What's Newton's second law?
F equals the mass times acceleration. Force equal motion.
Excellent. What is Newton's third law?
Everything acting on something is equal and opposite.
Awesome. Yeah. For every action, there's an equal and opposite reaction. Okay. Excellent. Just reviewing a couple of those. So then what about thermodynamics? What is the first law of thermodynamics?
Energy is neither created or destroyed.
Exactly. Energy is finite. We can't make it, we can't destroy it. We can only move it around or change it from one form to another. Um, because of that, if we have a closed system, we can calculate energy given heat and work, right?
Mm-hmm.
So for example, if I know that this particular reaction requires 700 kilojoules of energy, and I can measure the heat that was produced during the reaction, I can therefore calculate how much work was done. Um, Going back, can you describe to me what work is?
Work is the basically like what is being done to an object, like
Hmm.
how much of that is being done to an object.
Yeah, yeah, I like that a lot. So basically, it's the use of energy to do stuff, to do something to something else, right? Exactly. So in order to do literally anything, work needs to be done because energy needs to be expended. Work by definition, I believe, is just change in energy. Um, so if we are doing work because energy can't be created or destroyed, if we're in a closed system and we're doing work, some of that energy has to be lost, but in the form of heat. Does that make sense? Because no reaction is perfect at converting 100% of the energy from one form to another. It always loses some energy in the form of heat.
Okay. Anything gotta be lost. And then that's where Q equals MCAT comes in.
Q equals MCAT comes in when we're talking about the heat produced in a
Phases, different phases.
um more like um more like when we're talking about the specific heat capacity. So when we're talking about like the heat in a how do I put this? Oh gosh, I'm pretty sure you would use Q equals MCAT.
I
Mostly
know
for
that.
calorimeters.
I don't know. When I was reading, it was yeah, it was basically that. Basically, I understand that when you change phases like gas to liquid, gas to solid, temperature does not change, but heat is either added or removed. So, in order to know what change is when Q equals MCAT, we're essentially knowing what that change in temperature ends up being when it finally reaches the next phase.
You
But it's
can
always
absolutely do that. You can
has a
absolutely do it
specific
that way.
heat.
It,
Yeah.
I don't think that during the actual change would be that effective because the change in temperature is zero.
Yeah, it's always zero, but
So
when it
that, yeah,
finalizes to the
when it
next phase.
changes, yeah. Okay. Yeah, I think you could use it that way. I'm trying to think of how I've seen Q equals MCAT used. Um, I can't really I can't really remember very well. Most of the time it's just kind of a plug and chug. Most of the time that I've seen it used, they will give you the specific heat capacity of the fluid in question, and then you will use the um a mass that was given and any change in temperature to calculate heat or something like that. But the key between Q equals MCAT and Q equals CAT is that Q equals MCAT, you are using specific heat capacity. So it's the heat capacity related to the particular um, compound or the fluid being discussed, rather than heat capacity, which is a little more general. Um, so going back to energy, because of this, so energy can't be created or destroyed according to the first law. We know that we can calculate energy through some simple addition, work and heat released. Now, this kind of leads into the second law of thermodynamics. So why is energy not just equal to the work done? Well, because some energy is lost in the form of heat. So what is the second law of thermodynamics?
Disorder.
Okay, yeah, disorder. Entropy cannot decrease.
Huh?
Okay.
What's the last part?
Entropy cannot decrease.
Yeah. Mhm.
There's another point to this. Uh, heat cannot be completely converted into work.
Okay.
The idea that you can't turn heat into work in a cyclical process. In other words, renewable energy.
You can't do that.
No, there's only one situation where heat it that is released is actually like there's only one situation I can think of where you could even consider 100% of the work um being like a perfect conversion, and that's a space heater. Because a space heater turns energy into heat, and then the energy that is lost in the form of heat, which is still the purpose of the space heater. So you could kind of cheat and say that that is 100%, but that's not true. It's just it's it's just a nice little loophole.
Okay.
But yeah, the idea is that you can't convert all of your heat into work. So the heat that is lost during your energy expenditure cannot be 100% turned back, which means it's just going to be lost. And this is why there is an energy crisis, because we're losing energy in the form of heat, heating up a lot around, and then it can't be used. What is the third law of thermodynamics?
I'm sorry, what?
What is the third law of
There's a
thermodynamics?
there's a third one.
There is a third one.
Okay, no.
Okay. So the third law is um, that a pure crystalline substance at absolute zero will have an entropy of zero.
A pure substance will basically have an entropy of zero.
If it is basically a substance at absolute zero has zero entropy.
What does absolute zero mean?
Are you familiar with Kelvin?
Yeah, like zero Kelvin.
Zero Kelvin means that there is no heat whatsoever, no energy expenditure at all, no heat, nothing. It is absolute zero. Theoretically, it exists. We haven't been able to observe it physically. The idea is that at absolute zero, nothing can move because movement creates heat. Because movement expends energy, and that energy expenditure creates offloads some heat.
Okay.
So at absolute zero, if there's no heat, oh, excuse me, then there's no movement. And if there's no movement, then there's no entropy.
Okay. No movement, no entropy. Got it.
I don't really see the third law of thermodynamics being very applicable on the MCAT, but it's there. And then the last law of thermodynamics.
Where
It's
does
called,
three and four come from?
this isn't the fourth, this is the zero law.
Oh, okay. Yeah. Zero law. I remember that one. Um,
Do you remember what it is?
I don't remember, but I remember that I had to read it. And it was something about I don't remember. It was something about heat and the process of it, like temperature and everything.
Yeah, you're close. You're close. So it has to do with thermal equilibrium.
Hmm. Oh, okay. It was a scenario with a cup. So if you have a cup, basically, if you're at third, when things, it's not necessarily things touching each other, but basically a mug with hot water in it and a hot mug and you touching it, you're all at thermal equilibrium. So that means that you're at like zero. There's no transfer.
Yeah, no, that's fair. That's thermal equilibrium. So the zeroth law is basically the transitive property of mathematics.
Uh-huh.
If A equals B and B equals C, then A equals C.
Okay. Yeah.
So the zeroth law is saying that if we have object A is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then object A is in thermal equilibrium with object C. Does that make sense? Basically, they're
Hmm.
all in thermal equilibrium.
Yeah, and there's like no transfer, like they're all together.
Yeah.
Okay.
Okay. On this test, everything tends towards thermal equilibrium. Just rule of thumb.
Okay. So that matters.
Yes. It helps with some assumptions that we need to make sometimes. Okay. Um, I do want to go back real fast to the third law of thermodynamics. Not the law itself, just entropy. Um,
Mhm.
can you tell me what entropy is? Oh.
Disorder.
Okay, disorder. I like it.
Yeah.
So
That means that your what delta G is negative and your delta S is positive, all that good stuff.
okay. What's the formula that you're referencing?
Oh my goodness. Something about ghost. Is it ghost? Delta G equals.
You're very close, yeah. It might, you might be, what you're saying sounds pretty close.
H.
Delta G equals delta H
Mm-hmm. Minus.
minus T delta S.
Oh, no, then never mind. Minus T delta S. Okay. Yes, I know that one.
I think
Sometimes.
you could do it delta S times T too, which would be ghost. I like that. I like that a lot. Um, but yes, that's the formula you're referencing. We have
Mm-hmm.
entropy being disorder. I like that a lot. So so the disorder just meaning that if I have more particles, do I have more or less entropy?
Okay. The answer to that is more particles. Yes. I mean, more entropy. Not yes, more entropy.
Okay. Yeah, you would absolutely have more entropy because the more particles there are, the more disordered it is, quote unquote. Um, so if I increase the speed of my particles, do I have an increase or decrease in entropy?
Increase.
Yep. They're more likely to move around, they're more crazy, they're doing all kinds of random stuff, increase in entropy. If I increase the volume of my gas, am I increasing or decreasing entropy?
The volume, like how much gas is in there.
Well,
Um,
we have the same number of particles of gas, but I increase the volume of that gas.
oh, decrease
Why?
because you made them bigger. That's what I'm looking at it as.
Okay. So for that one, what I like to think about is this. So if I have a closed container here,
Hold on, you're drawing. Mine is on too.
oh yeah, can you see my screen okay?
Yeah, I can.
Okay, okay. So if I have a closed container here and I have these, I think 12 dots, these are my gas particles. They're moving all over the place. And then I go over here and I give them even more space. They're now more free to move around, even more. So with entropy, I like to think about a toddler. More so now than ever because he is a little cyclone.
Mm-hmm.
So I like to think if I give my toddler, like, if I just lock him in a bathroom, which was not ethical, don't do that. But if I locked him in a bathroom, how much damage could he do? Quite a bit, you
Mm-hmm.
know.
But if you
But
locked him in something bigger, he
yeah,
can
if I
do
gave
even
him like
more
an entire
disorder.
living room, he'd be able to mess up even more.
Mm-hmm.
Entropy
Okay,
is the tendency towards disorder, so
gotcha.
or randomness or chaos.
So when you're saying more volume, basically more space, more disorder for the particles.
Exactly. With a
So what?
gas, when you increase volume, you're not increasing the number of particles, you're increasing how far those particles are spread out.
Okay, so my question. Okay, my next question is, what did you ask me before more volume? If you increased more what? Gas?
Particles.
You asked me three. One was
Oh,
particles, one was volume, and one was something else. Or did you not exactly?
speed.
Speed, speed, speed. Okay.
If you increase the speed, yeah, that increases the entropy as well. Um, what about temperature? What happens if you increase the temperature?
More disorder.
Or
It's heating
disorder.
up.
Yeah.
Yeah, heating up.
So, are you familiar with how temperature relates to kinetic energy?
Yeah, in a bit.
Okay. So, kinetic energy as it relates to temperature, are they um inversely or directly related?
Inversely.
So,
Why
your
are they
suggestion
inversely?
is that an
No.
increase in kinetic energy is a
Pressure.
decrease in temperature?
Pressure is inverse temperature. Um, what is inverse temperature? Pressure, I think. Kinetic energy
Let me
is
ask you this. Let me ask you this.
mhm.
Do you know the definition of temperature?
No. Temperature
Okay.
equals
So then let me ask
temperature.
you this. What happens to water when we heat it up?
It gets hot.
Yes, it gets hot. And
Boil.
it boils. So boiling is the conversion of liquid into
Gas.
gas. So what's the difference between a liquid and a gas as far as the particles are concerned?
Temperature.
Temperature. Well, kind of. So what are the
The
particles
heat
doing?
added to it. Oh, they've changed what form and spread it out or something like that.
Exactly, exactly. Yeah, yeah, yeah. So if this is a solid, all of the particles are very close together.
Mhm.
This is a liquid. This is a gas. Does that make sense? We're
Mhm.
spreading the particles out. Now, with spreading the particles out, the reason they spread out more is because they're moving more rapidly. So the faster your particles are moving, the more likely they are to convert to gas. So when you add heat, you're exciting these particles, making them move faster. An increase in kinetic energy
You're increasing temperature.
is an increase in temperature. The definition of temperature is average kinetic energy of your particles. So if I increase temperature, I'm increasing kinetic energy. If I increase kinetic energy, do you know what the formula for kinetic energy is?
1/2 mv squared.
Can mass change?
Mm. Of the particles? Mhm.
Yes,
Yeah, yeah. Because the same weight in a gas is not the same weight in a solid, right?
but the particles can't
Or
change in mass.
okay. So the mass can't change? Okay.
Correct. Also, the mass, what's the difference between liquid water and gaseous water as far as their molecular structure? What's the difference between H2O liquid and H2O gas?
I don't know.
The only difference is speed.
Oh.
So the molecule itself is still 18 atomic mass units.
Mhm.
So its mass didn't actually change. The only thing that changed
Yeah.
is its speed. Mass is constant. The only time mass can ever change is if you manually change it, like if you add or subtract mass from the item. Um, which like working out, for example, we can change our mass, but that's only because we are exercising and losing mass in the form of um uh like breathing it out as CO2 or um defecation or etc. Sweating it out, what have you. But that mass has to go somewhere. With um molecules on the MCAT, mass is going to be constant. It does not change. So in kinetic energy, since mass is constant,
Sorry. Uh-huh.
the only thing that can change is velocity. So kinetic energy is describing movement. Kinetic means movement. Kinematics are the equations that have to do with movement. Kinesiology is the study of movement. So kinetic energy is movement energy, as opposed to potential energy, which is the energy that is able to do something, the energy that's kind of like waiting. Or in other words, it's the energy that's not moving. So kinetic energy directly relates to the temperature. The faster something is moving, the more kinetic energy it has, the more temperature there will be.
Mhm.
That's another reason why, like moving your arms very quickly produces a lot of heat, produces a lot of produces a lot of heat. Moving your body real quickly, going for a run, doing anything like that, moving more quickly produces more heat because you're increasing the temperature, you're increasing the speed of your molecules, you're increasing the speed of the molecules around you. That's going to increase the temperature, and it's also doing quite a bit of work, which is going to release heat as a byproduct. All in all, increase in temperature, increase that movement, increase that kinetic energy. All of this leads towards an increase in entropy, right? Because it's more likely to be chaotic, more likely to be disorder, more likely to be random. Um, which one would you say has more entropy? H2O or O2?
Oh, two.
Why?
Less is more. Um, what's that now? It's more disorder.
So which one has more entropy out of these two?
Right?
Okay, why?
Because it has more particles.
That's right. So out of these two, which one has more particles?
Uh, so,
H2O. Yeah, there's just more components to H2O. So if I break apart O2, I end up with two particles. If I break apart H2O, I end up with three. So H2O actually would have more entropy inherent to it than O2. Now, there's a bunch of other factors that go into it, but this was just an example. So the more complexity there is, the more entropy there is. Okay. Similar to like a toddler breaking stuff. If I have something that is made out of um, just one sole piece, it's gonna be very hard to break it because it's one piece. But if I have something that's made out of multiple pieces, then it's more likely to get broken, right?
mhm.
All right. Entropy. Sweet. I feel like entropy is pretty well understood here. Let's talk enthalpy. What is enthalpy?
Changing heat.
Did you say change in heat?
Yeah, that's right.
Yeah, yeah, I like it. I like it. Yeah. It's basically you're breaking or forming of chemical bonds.
Yeah.
So delta H, I like to think of is energy ugh, within bonds. So if I have O2 and it has an enthalpy of, I don't know what the enthalpy of O2 is. Let's just say that it's 25.
Mhm.
That's ridiculous, but let's just say it.
Mhm.
Then it requires 25 joules to break O2. Um, yeah. So enthalpy is just the energy, like you said, the change in energy or energy within bonds. I like the energy within bonds more just because a lot of the times we'll see something like a positive delta H versus a negative delta H, and it can be kind of confusing. So what I like to think about with this is that a positive delta H means that we are adding energy, and a negative delta H means we are losing that energy or it's being released. Now, is energy released when a bond forms or when a bond is broken?
Broken. Energy is put in when a bond is formed.
That's what I thought as well. That's to me what made sense conceptually, but it's the other
Mhm.
way around. When a bond forms, energy is released.
You're basically using energy to make the bond, but when a bond is released, it's no energy to release it.
No, you need to put energy in to break a bond, but when a bond forms, it releases energy.
So, it, so when you break a bond, it releases energy. But when you form, it releases energy. When you form a bond, you have to put in energy, right? Or am I saying it backwards again?
I didn't hear it, sorry.
When you break a bond, you're releasing energy. You're
No,
using energy to break a bond.
it absorbs energy.
Okay. In order to break a bond, you need to put in energy to break it.
Mhm. Positive enthalpy.
Okay, I'm gonna write this down because it's not falling in my head.
It doesn't make very much sense intuitively. So I have to use like weird ways to remember it. So like I think about a bowling ball. If I want to break a bowling ball, I have to add a lot of energy in order to do so, right? It's not just going to spontaneously break. So putting energy into breaking something, to me, that makes sense, kind of. Then it goes, okay, well, when a bond comes together, how does that release energy? That one's tough. So I kind of have to
Add
just think about the other.
energy, add energy to break a bond.
Add energy to break a bond, exactly. Release energy when a bond is formed. So that's why we say positive versus negative delta H. Positive means we're adding that to the system. Negative means it's being released. Does that make sense?
Yeah, the positive and negative makes sense, but
Okay.
releasing a bond.
The way I like to think about this is that energy is stored within bonds. So when a bond forms, energy is kind of like, how do I put this? Unfortunately, like the only thing I can think about is like ribosomes. Are you familiar with like the 30S and the 50S ribosome subunits?
Mm-hmm.
So if this is like the
Uh,
30S and this is the 50S, together, what S do they make?
like 70 is what you're trying to
Yeah,
say? Like
exactly.
adding?
Exactly, which is dumb because it's like 30 and 50 makes 80. Well, yeah, but when they come together, they're actually like overlapping.
Hold on, wait, how did I thought that was 70?
What? No, I
It's
think you're right.
yeah,
Hold
yeah,
on.
it is 357. I just said 70 based off the top of my head, not counting them. Yes, 357.
Yeah, no, you're absolutely right.
Okay. Yeah,
But
yeah, yeah.
normally you would think 30S and 50S would make 80S, but it doesn't.
Ah,
And it's
okay. I
because there's
never
some
thought about it as
overlap.
adding. Okay.
Yeah, and there's some overlap with it, right? So that's why it
Mhm.
actually makes the 70S. So that's what I like to kind of think about. When I have the 70S, if I separate them out, there's some of this space in between that is now going to be kind of like new added mass to our system here.
But when you
So,
build it, you're removing 10 of that like mass from like putting them together.
mhm. So it's almost like energy is released or the size is released when I put them together. Whereas when I break them apart, I add to them. That's kind of what I think about, which is weird because that's it in and of itself not a terribly well understandable, like
What
easily
about
understandable thing.
relationships? I could think about it
I
like
I
relationships.
do so that's what I do. Sometimes I can the best way to remember things is if it can be a little bit more crass. So sometimes I think about it in terms of um when a couple comes together, there's a release of energy. Um to me
I
that's
understand.
intuitive. So that makes a lot more sense to me.
I
Um
get it now.
so and it takes energy to break that apart. Um So I think that makes a lot more sense. Um, so enthalpy, super high yield. This comes up all the time. And you've probably seen stuff like heat of formation, heat of combustion, heat of fusion, etc. Or heat of reaction, like delta H reaction. That's saying like that this is the amount of energy to either form or break a particular bond. So like the heat of reaction for um let's see, for like CO2 to O2 plus C or something like that. There would be some sort of heat of reaction for that. It would be like, I don't know, like 1500 kilojoules or some nonsense. I don't know. Um, but then that would say that in order for the CO2 to become O2 and C, we're breaking that bond. So would it be a positive 1500 or a negative 1500?
Huh?
Okay, so heat of reaction is the enthalpy necessary to either form or break bonds. So
Uh-huh.
if I had the heat of reaction for CO2 becoming O2 and C, And I said
It's
that it was
positive
1500. Why positive?
because we're breaking the bonds.
Absolutely. That's the heat of reaction. Does that make sense though?
Hmm.
Okay. Is this clarifying? Like I'm sure you've seen heat of reaction before. So is this kind
Yeah,
of making that make a little bit more sense?
more sense. Yeah. Okay, hold on. I gotta write this down because I do be seeing it and I just be like, okay, this is what this is. That's it.
Okay.
All right, thank you.
All right.
Alrighty. Is there more?
The last thing, well, so there are like heat of formation, heat of combustion. Um, if I have a very stable bond, is it easy to break or more difficult to break?
More difficult to break if it's stable.
Exactly. So would I need more or less energy to break it?
Breaking bonds. I need more energy to break it.
Exactly. Think about like a relationship again. If you have a couple who are very, very stable, it's harder for that relationship to break. So that's discuss like when we're talking about the heat of combustion is like the enthalpy related to breaking a bond. Particularly O2, and some sort of a biological compound in order to form CO2 and water. So a high heat of combustion is
Mm-hmm.
associated with an unstable molecule,
Mm-hmm.
and a low heat of combustion is associated with a stable molecule. Now, let's talk delta G. Delta G is Gibbs free energy, right?
Yeah.
So delta G is just the what can you tell me about delta G?
Negative is entropy.
Um,
Um, yeah, that's all I got because I didn't watch the video. I only read the book.
that's okay. So negative is entropy. Um, so are you saying that if I have a oh, excuse me. Oh. Are you saying that if I have a negative delta G, that means I have a high entropy?
Yeah, and more disorder.
Yeah, that's typically how it works. So delta G is the energy available to do work. Basically, how useful is our energy? Um, if I have a negative delta G, that means spontaneous. Negative delta G, remember going back down to here with a positive delta H and a negative delta H, positive delta H means that we add energy to the system, right? And negative delta
Mm-hmm.
H means it's releasing that energy. A negative delta G means that the system is spontaneous, or the reaction is spontaneous
Mm-hmm.
because we're releasing that energy.
Mm-hmm.
If we're releasing energy, that means that um something whatever is if we're releasing free energy, so delta G, that means that the reaction would happen regularly. You don't have to do much for that to happen. It's already tending to release that energy.
Mm-hmm.
If it's a positive delta G, it means that it's not spontaneous. It needs a little kickstart. Energy is required to get that system to form that
Put in
reaction.
work.
Exactly. You need to put in work. You need to put in energy. So you said if we have a negative delta G, that's probably a very high amount of entropy, and that's probably true. Because if I really increase this number right here, that's a negative sign in front of it. So if I really increase this, this is more likely to be negative. Does that make sense? If I subtract a large number, I become more negative.
Gotcha.
Yeah. Now, it's possible that I have a really high entropy, but I can have an even higher enthalpy.
Mm,
So even if I have a big entropy, if I have a sufficiently large enthalpy, I could technically be positive delta G. That doesn't happen very much, but it is theoretically possible.
okay.
If delta H is positive and delta S is negative, what is the sign of delta G? Like, is it negative or positive?
It depends on the numbers that is positive and negative.
Well, if we know that delta H is positive and we know that delta S is negative,
Positive minus a negative equals a positive. Yeah. So it's gonna be a positive delta G.
exactly. And that's not very spontaneous. And that makes sense, right? Because a negative entropy, does that mean that we're becoming more ordered or more disordered?
So more ordered.
More ordered. And do things tend to be more ordered or tend towards disorder?
Things like to tend towards disorder.
Exactly. So if we're becoming more structured, that's relatively unnatural.
Yeah.
So we're going to not be a spontaneous reaction. It's more likely that we're going to need to put energy in. Think about like a bedroom. Bedrooms get really dirty very quickly, like very messy, or living rooms or whatever have you. Things get messy very quickly. You don't have to put effort in to making a bedroom or a living room messy or a kitchen. You do, however, need to put energy in to clean it up. So it's more spontaneous for things to become disordered and more spontaneous and less spontaneous for things to become more structured.
Mhm. Yes.
All right.
It's more natural
That
disorder.
this is your fundamental thermodynamics relation equation. Delta G. I like the idea of
Mm-hmm.
ghost actually. That makes me very happy. G equals delta H minus delta S times T. That's cool. Um, there's one more equation that can be useful here. Similarly, delta G naught equals negative R T.
T L N Q.
Yeah. Do you know what this is referring to?
Logarithms.
Yeah, okay. So the natural log is there, so we definitely dealing with logarithms. KEQ is the equilibrium constant.
Equilibrium. Mm-hmm. And then the R is the constant. What?
Um,
1.84 or something. 1.48, something like that.
Oh yeah, I'm gonna be real. I don't remember what that one was.
But it's a
4.184?
yeah. I feel like that's specific heat. That's C for Q because MCAT.
That yeah, that might be C. That might be specific heat for water.
But I think R is a constant, and it's right. Like R is a constant, correct? For
Yes.
RT, L, and Q. Yeah, that's
Yeah.
so that's one, and then T is temperature.
Yes. Nice. Um, yeah, this is just how we combine Gibbs free energy to the equilibrium constant. Okay. I don't really see a lot of application for this one on the MCAT. I typically see it's more of a plug and chug. So I think that that is good. The last thing I want to talk about with this is kind of related to heat. Can you tell me what are the three kinds of heat exchange?
Uh-huh. Okay, because I just looked at them, but not looked at them. I know the first one is conduction. That
Conduction.
is transfer of heat via collision. The third one, don't remember the name, but it's the transfer of heat via EM, electromagnetic, that
Radiation.
radiation. There we go. The third one is the transfer of energy via the second one, which is the other conduction, something, and then the third one, kind of something. Second one is the transfer of energy, not via, I don't know, it could be closed space or it could be, don't
This one
remember.
is this one is
Fluid. Dang.
convection. So,
Yes.
um, does heat stay low or does heat rise?
In the fluids of
Mhm.
convection,
In fluids, yeah.
uh, in the movement, I would say rise.
Yes, heat rises. Um, think about a hot air balloon. With a hot air balloon, we put fire up in the balloon and it heats up the air, causing the balloon to rise. This is also why top floor apartments are hotter than bottom floor apartments.
Heat
This is
rises.
why, yeah, top floors of homes are typically more hot than a basement.
Lower. Mhm.
Yeah, and this is also why in the water in like a lake, um, as you dive deeper, it gets colder. That's called convection.
Mm,
Fluid that is hotter moves towards the top of the fluid, and fluid that is colder moves towards the bottom. The reason for that is because of gravity and density. If I have something that is like particles moving like this, but relatively slowly, and then I have particles really far away from each other moving more rapidly, which one of them have more energy? The top ones, these three, or these three?
the one moving more rapidly.
Yeah, exactly. And because they have more energy, they have more temperature, they're hotter. So if they're moving more rapidly, they're farther apart. And if they're farther apart, they're less dense.
Density.
Does that make sense? Density is mass over
Mhm,
volume, right?
mhm.
What we've done here is we've increased the volume. And if we increase the volume, but the mass stays the same, what happens to density?
It decreases.
It decreases. And if it decreases, it tends to be above the denser stuff. So the colder the fluid is, the slower it's moving, the slower it's moving, the smaller its volume, the smaller its volume, the greater its density. The greater its density, the lower to the closer to the bottom of the fluid it is.
Wonderful.
That's convection. And then you're right, radiation is the concept of like
Electromagnetic wave.
releasing energy to the environment, releasing heat into the environment. We do that. That's why we show up on infrared because we're releasing infrared energy just by existing. And then conduction, you were right. It is the collision and transfer of energy amongst colliding particles. Um, excellent. I think you have a very solid understanding of thermodynamics, which is awesome because most people don't. How are you feeling about thermodynamics?
Yeah, pretty good.
Good, excellent. Um, do you have any questions for me about anything?
No, about anything. Yes, other stuff. Hmm. I'll just do fluids and electrostatics today. I'll increase my studying to 3 instead of 2 because I think I could do it. My
Okay.
hours. Um. No questions. Still reviewing, right?
For right now, yes. I think you absolutely, if you yeah, right now I'd say still review. What we could do
My
is
Anki isn't working.
your Anki is not working, right?
Let me show you my Anki. Let's see it. Can you see?
Yeah, I
It's
can
0.
see.
You see all these zeros?
Yeah, can you click on browse?
I have to go into it. And then click on browse. And then what do I do?
Uh, I've never seen that function on an iPad. Um, go back to your main Anki decks, like all to see all of your decks. Oh, sweet. Uh, do you not have a browse function from here?
Do I need to update it?
No, that shouldn't be it. Let me open up my Anki and see. So I use Anki on my PC. Um,
I have Anki on my PC too, but that's what gave me the virus.
you have a virus?
Yeah, because I was trying to connect my 8-bit and I was looking on YouTube, and one of the YouTubes made me download something that caused a virus on my PC. So
Ooh,
like even like in the middle of our session, it will pop up
I'm so
like just
sorry.
randomly. Yeah. So annoyed.
Okay, so this is what I see on my Anki. I'm not
Because
sure. So up here, I have this browse function.
yeah, like when I go into mine, I have that browse function.
Oh, sweet. Yeah. So if you open up that browse function,
Mm-hmm. Where it going?
yeah, I'm gonna go back to here. So I have this. So I can see my current deck. I can see all of my different decks. Um,
There's
if you
nothing in my current deck.
there's nothing at all.
Yeah,
Wow.
like that's what I'm saying. Like I finally was able to download it, but then there was nothing that was in it. I don't know if I downloaded wrong. Uh,
Interesting. No, I don't know. I think that if you do the mile down, that should be fine. Do you have access to the mile down and are those
Okay,
cards there?
so then we go into miles down, and I tried to do the thing where I locked it. What is it called? Where he showed me closing them,
Hmm.
suspending.
Yeah.
So then I tried to like type in kinetics, right? And then 38 pop up, I type in kinetics to search, then 38 pops up, and then I'm trying to select all, and I press toggle suspend again, but they
Mm-hmm.
won't unsuspend so I can study them. It still says 0 decks.
Huh.
Yeah. So like if I select everything and I toggle suspend, then I get my all 316 back. You get what I'm saying? Let me show you.
Yeah.
So like this is me. Hold on. Let me see if I could look on my screen while showing you at the same time. Hold on. The position. So I go to physics.
Mm-hmm.
Just, just backwards. Give me a minute.
It's okay.
Then I go to browse. I select all and then action. And I toggle suspend. So now I go back and I have nothing, right?
Yes.
So then I go back to browse. I type in kin-
Kinematics.
kinematics. I typed in kinetics. There was no kinematics.
Okay.
They want me to do that. No, so it's difficult. Give me a moment.
That's okay.
Kinetics. Search. So now that's 38. So then I toggle, I select all, I do action, and then in my action, I try to toggle suspend. Oh, hold on. Select all, do action. If I toggle suspend, then I go back, I still have 0 in my deck. If I press toggle suspend again. You get what I'm saying?
Mm. Mm-hmm.
So now I don't know what to do. Should I put reset? I don't want to reset. I'm scared.
No, so go back, so click on, like, highlight just one card right now.
Hmm.
Now click actions and toggle suspend. And
Okay.
then exit out and see what that does.
Nothing. Zero. Zero cards. No cards whatsoever.
Yeah, that's weird. That's really weird. I'm not sure why that's doing that. But to be honest, I'm not familiar with how Anki interacts with iOS. I don't know if that's a factor here. I don't know if it's something else. Um,
I'll just search it up on YouTube. Hopefully I don't get a virus on my hand.
don't download anything. Just, yeah, no, I'm not too sure how it works right there. I've never had problems with suspending or unsuspending on PC. I don't know how that works right there. I'm so sorry. Um, I can try to look in and see what the consensus is online as well. See if anybody has some advice. Okay.
I guess I could do it. But I don't know why the on is like completely like 0.
That one doesn't make sense to me. I don't know what's going on with that.
I had to go onto my on on my PC.
I wouldn't worry about the on king for right now though. Milestone should be
Okay.
good.
I just wish that I could like make it specific to the things I'm doing.
Oh man, I do too. I don't know what's going on with that. I'm gonna try to look into it a little bit more and see what I can find, okay?
I could probably do it on my PC. Now this wants to glitch, but hold on, let me go.
Okay. Let me know if you
Yeah,
can if that does work. If not, I can look into it more.
yeah,
Um, but for right now, are you still okay to do our meeting on Thursday in the evening?
yes, 9 p.m.
Is that the time you want? We can absolutely do that.
Oh, which time did we quit? Yeah, yeah,
I
9
think I
p.m.
think that's
That's
the time we
fine.
put. I just wanted to double
Yeah,
check.
yeah, yeah, yeah.
Okay. Let's
That
try that out and see
that
if
works.
how that works. Okay.
Yes, sir. I'm trying to change my work schedule, but yeah.
You're all good.
Mhm.
Then I will see you on Thursday, okay?
Let's see.
All right. Bye.
Oh, I do have a
Oh, what's
question.
up? Yeah, yeah.
How do I unsuspend from how do I unsuspend it on a PC? Toggle that?
Um, yeah, if you highlight whatever you want to highlight and then
Mm,
right click toggle suspend should be an option. Or I believe it's Control J.
Control J. Because I got toggle mark. Okay, thank you.
Okay.
All right, have a good
All
day.
right, see you later.
Bye.
Bye.